Hello, welcome all of you at the last presentation of this meeting. I hope you're not going to fall asleep during it. I try to be as energetic as possible. So I represent Academic Computing Center Cyfronet from Krakow in Poland. We have over 40 years experience in HPC and delivering computation services to Polish scientists. We do also some networking. We also do some services like cloud computing, like shared hostings for the scientific community, but mostly we focus on HPC. We take part in different international projects. We are also coordinating a big national Polish project called PL-Grid, which focuses on delivering unified computational services for the whole Polish scientific community. In terms of our HPC resources, currently we operate 3 computers. One of them is pretty old. This is Mars, which is an IBM cluster. We also operate 2 HP machines, Zeus and Prometheus. Prometheus has been installed this year, and for its use, the data storage system which is implemented just comes from DDN. So in terms of our usage and things we do on our computers, we provide free computational resources for the Polish scientists, so we don't have or have very little influence on what actually is being done on our machines. Most of the users do some chemistry and physics science. There are also some groups doing things like genomics, which is very data intensive, as you probably all know. We have a lot of groups doing medicine, which also involves a lot of data processing. So our storage infrastructure is currently looking more this like this currently. So we have 3 computational machines, and of course each cluster, each supercomputer has its own scratch system, which needs to be first of all very efficient in delivering the data to CPUs. We also need to have some home directory for the users. We also need to have some midterm storage for project files. As we do some computations for large scientific communities, large international scientific communities like WLCG, which focuses on computations for the LHC data coming from CERN. As for CTA, which is Cherenkov Telescope Array community doing some astrophysics, they require a different set of protocols to access their data, and these are these 2 entities named grid storage. I'll elaborate a little bit later on. And we have some tape libraries to provide efficient backup and, let's say, deeper archive. So in terms of grid storage, this is something which is probably not very popular among the scientific community. What you might be familiar with is the grid FTP protocol, which is widely used for data transfer over wide area networks. But as I said before, there are some groups like LHC, like CTA, like the Linear Collider, like BEL, which is a high-energy physics experiment from Japan, which we work with. So our users are part of these communities, and we provide resources for them. And they require a dedicated set of protocols. Like the basis for them is SRM. This is Storage Management Protocol, developed in WLCG some time ago, which basically wraps some basic protocols and that additional features like type of the storage, like its location, copies, and so on. So we need a dedicated storage system to provide all of this. It works on top of POSIX file systems, but it doesn't expose really the POSIX functionality to the clients. So for the characteristics, most of the files are quite large. They are over 100 megabytes per second. So from the storage administrator perspective, it's pretty nice. Most of the files are already compressed. They are pretty well prepared, as the communities have awareness of the data. They actually know how to use it. It's very hard to do some deduplication because they usually don't repeat the data inside. And from the access pattern perspective, it's really very straightforward. It's mostly sequential. They would mostly read the whole file, analyze it, or stall the output. So for this, some time ago, we've been using traditional disk servers, traditional JBots, and we decided to replace this last year with modern DDN hardware. In fact, what helps is the amount of disks you can actually put into the DDN disk array, which is enormous. It's over 1,600 disks. In our case, 844 terabytes drives were totally enough to fulfill all our storage needs. And now, instead of having a bunch of servers, bunch of JBots, we just have one nice big box of storage to which we can connect our servers and expose the data further on. Yeah, so what's also specific with such usage is that it's really hard to predict how much data you're going to actually need, because you have some commitments you need to fulfill, you have some short-term, long-term plans, but it also happens, and probably this is somehow special to our center, that the users come somehow unexpectedly. They require resources of hundreds of terabytes, and we need to address this somehow. And as we are a public institution, we cannot just go to the vendor and buy some hardware. We need to follow all the formal procedures, tenders, and public procurement, which usually takes a lot of time. So we need to over-provision the resources we buy, of course, to some reasonable point. And that's why not all the disks are fully populated. If we will get to the higher occupancy of the storage, we would just need to proactively buy some additional hardware. So this is the one kind of storage we do for our computational resources, and this is site-wide for all of the computers. The other thing is POSIX storage, and this is something I think closer to all of you. So this is both for fast temporary scratch storage. This is also for project files, for inputs, outputs, and analytics, the data to be analyzed. And of course, everyone is talking now about getting rid of POSIX, which is a great idea, and of course I agree that it creates many obstacles for the scientific usage of data. However, it's really not going to happen in the next year or 2 years or probably even 10 years, even though we all wish it to happen, to go away. But user not being unable to do LS is a very unhappy user, and we don't want unhappy users. So we have different solutions, and there are on the market even more solutions which address all the needs. So as you were able to see before, for the home storages we use NFS because it's very simple, it's straightforward. We use both software and some hardware implementations. We've been using GPFS for Zeus machine. Now with Prometheus it's only Lustre, and I will also mention maybe a little bit more of this further on. So for our Lustre experience, we've been starting to use it in 2008, I think, with Lustre 1.6. This was a proof of concept system for Zeus machine, which was then changed to a production system on the Mars cluster. Basically, it's rock solid. We don't need to touch it. It's working ever since. These are the machines which get the most uptime on our clusters, so it's pretty nice. It's a little bit different with the new branch of Lustre, with 2.1, which we have started using just after the Sun One Cloud thing some time ago. So we were one of the first users of 2.1 with a very early development release, with the whole awareness that we are probably going to face some issues, and yeah, and we faced them. So we did some input on the further development, I think. As for a very small institution, it's really nice. So the second production system for Zeus, which is working now, is a little bit faster, based on 2.5. We do our own builds, so we just gather the patches from the whole community, from the Git, and try to build and select them in a more stable way. So what's a big advantage of Lustre over GPFS? There are of course some technical differences. GPFS is much more feature rich, Lustre is much more simpler, but on the other hand a bit faster. But what's a big value for us is that we can actually understand what's going on, at least to some point with Lustre. with GPFS, it's not as easy. It's very hard to get some fixes. So that's why we decided to move to Lustre and stick to open source as much as possible. So with the new machine, which was going to be purchased last year, we knew that we are going to need some storage. We decided that we are going to announce a separate tender, a separate procedure for the storage. So I know that it's quite common to usually do it with the machine, and it would eliminate a lot of problems we actually had in the during the installation process. But on the other hand, we think that this gives you much higher flexibility. You are not locked down to a certain vendor which cooperates with the other vendor. So we think that it was a good decision from the perspective. So our general requirements was, of course, that the system needs to have high availability. It needs to provide some performance and some size. Now, with the performance and size, it's not so easy because it's really hard to estimate your needs. I don't know what's the general rule, but I guess that everyone is doing some guessing to some point based on experience, based on some expectations. So our numbers were based mostly on our experience, but it's really hard to say whether they are enough or not enough or too much. This will probably be clear when the machine is going to be decommissioned. So we decided to have two separate file systems, one file system for temporary storage for Scratch data, the other one for storing mid-term data, so project files. Yeah, this is a pretty picture of the machine. This is a HP Apollo 8000 system with a quite strange topology. I mean, it's not really very common, probably. We use island topology, and each island is a full non-blocking fat tree. The core network is somehow a mixture of tree and a butterfly network. It would need a detailed graph to actually explain it, but what's important is that we have 8-to-1 blocking from the islands to the core network. All the storage is located in the service aisle, and there's more than enough links to get all the performance we need. At least on the graph, it's enough. So for the RFP requirements, we wanted to have 5 petabytes of usable space for both file systems, one of them 120 gigabytes per second, the other one 60 gigabytes per second. We also decided that we are going to give some additional points for things like number of disk arrays, which is quite important because there are some vendors who offer you very small boxes, but dozens of them, which is a nightmare for the administrator. And also it's not really good for the availability. So the other points were for performance and additional capacity. The solution proposed by DDN, which actually won the tender and is implemented now, consisted of 2 blocks, so 2 file systems, each built from simple building blocks. For the Scratch file system, the building block is DDN SFA12K with 5 enclosures, 400 disks, and 4 OSS servers. So we have 4 building blocks like this. Additionally, of course, 2 MDS servers, and one of the disk arrays contains also disks for the MDT. And this is 120 gigabytes per second, slightly overperformed after some work being done. The other one is Archive, also building block construction, just the building blocks look a little bit different. They have more enclosures, less controllers, and we use 6 terabytes drives inside, which is enough to get us to the performance level of 60 gigabytes per second and 5 petabyte capacity. That's the picture of the system. It's really hard to get a proper angle to have a better one, but you can browse for the pictures on the internet. Now, what was previously mentioned, I think, by the KTH presentation is the dual LNET configuration and the trick which is being done to omit the limitations of Lustre with multi-InfiniBand connections. So what's being actually done is that each server has two separate LNET configurations. OSTs are bound to the LNETs, so divided equally by the two LNETs. And then each of the clients needs to be, of course, present in both of the networks. This allows you to actually get much more performance from the single server, so reduce the amount of infrastructure you use. And this is something which DDN proposed, and we actually like the solution very much because it's quite simple in implementation and allows you to max out the performance from the hardware. Now for the implementation, the performance numbers during acceptance were of course met. They were even slightly overperformed. And I think that there's still some work which could be done to improve the performance. The problem is that we had a very long and painful fight with the fabric and actually getting the performance out of the InfiniBand network. This is because of the topology I showed you before. It occurred that it's not really that easy to saturate the InfiniBand links. And as I said before, this was a separate project than the computing part, then actually the whole responsibility for this lied on us. So we did put a lot of work to actually make this done. There's still some improvement possible after some recabling. We could squeeze out even more performance from the system. With the multi-LNET configuration, there's a small glitch with TCP network, which is also implemented in the system. So we have two LNETs for InfiniBand, and we also have additional one for TCP network. And actually launching TCP network causes some breaking of symmetry in the InfiniBand LNETs. So this is also being resolved now by DDN. We've been also doing testing of the new DDN client for CentOS 7. It's working fine. We don't have any issues, and the machine is running CentOS 7, so it's really fine. For the future plans, we of course would like to solve this multi-LNET issue. We would like to recable the network to get even more performance, and this is something which we know how to do, I think, for now. We also have already the hardware for Robinhood and for HSM integration. Now we have a different procedure for the tape library, for the deep storage, deep archive. So we hope to have this done in the end of the year. Yeah, and a really nice feature which was on the Lustre roadmap since the presentation we saw just before was Project Quotas, which was developed by DDN, I think. And we really like the idea, but for some reason I think it's just, the idea just died, so yeah, that's it. Thanks.